This is a practical example of the work in NMR lab without theoretical background. So here in the lab, you can see a spectroscoper near the computer, you can see a permanent magnet, and for sure, because we're in Italy, you also can see a coffee machine. And now we will do a sample preparation. It is very easy with this type of NMR. So because we are working with a liquid sample, we need a pipette, and we will be measuring milk. And we need a 10 millimeter glass tube. So now I will put a milk into the glass tube. We need to be careful so there is no residue on the walls of the tube, as this could influence the measurements. So usually we fill up to 1 centimeter in height of a sample. And usually we want to prevent the evaporation of the liquid, so we closing the glass tube with parafilm. And also, if I'm running multiple samples, I sign them, so later on I understand what I'm measuring exactly. So now let's put our sample into the probe. Here we have a 10 millimeter probe. The horizontal lines on the probe indicate the homogeneous region in which ideally the sample should stay, so the measurements are recorded correctly and we have high and good signal. As for now, there is nothing magical about this. We have this rubber band which will move up and down, so we can place our sample in the needed region. And now, as we've done it, we can switch on the computer and we can switch on the instrument. And now we open the program to run the measurements. And we start with tuning and matching, which is used to optimize efficiency of the pulses and to maximize the sensitivity. The procedure for tuning and matching might depend on the instrument. For example, in this instrument, we need to manually move the cables into the needed position so we can perform tune and matching. But in some equipment, it could be done automatically by just clicking the button, so you don't have to change the cables. So now we need to align the dip that we have with a crisscross between horizontal and vertical lines, so we have the best signal possible, and I'm doing it by screwing these small screws on the probe. And when I'm satisfied with the picture, I can move the probe with the sample into the permanent magnet. You might not see it really clearly, but inside there is a lines also indicating the most homogeneous part of the field. And now, after these steps, we can start the measurements. We usually start with S1P. It could be called differently in different softwares, but it's just 90-degree pulse. We start with this to optimize the parameters to have the best signal possible. So here we have a list of parameters. Some of them depend on the sample, some of them don't. For example, maximum scan does not. It's just how many times we will run the experiment. Other important parameters that are different for different instruments is the dead time. It's basically the time the instrument needs to wait before acquiring the signal. Here we set in the offset and the phase to 0 in order to achieve the best picture possible. Also, it might be different in different instruments, but usually before acquiring the signal, we do this procedure. The parameter that depends on the sample is recycle delay. It's the time you wait between scans, and it depends on the sample. Usually for liquid samples, it is quite long, so in this case I put 4 seconds. So if we have 8 scans and 4 seconds, it basically means that we need to wait half a minute for 8 scans. Here I just made the video much quicker in order not to spend minutes on this, but all of this is just a procedure to start with the best parameters possible. And now we are choosing CPMG, the sequence to achieve the relaxation time, which shows us the behavior of water molecules inside or environment in which water molecules are in our sample. There is also a list of parameters that we need to change, and it depends on the sample and on the hardware of the instrument. So we start by changing these parameters, and again I don't put many scans only because I'm starting and I want to see if the signal is good or not. Here with the CPMG, we want for the curve to reach 0. If it's not reaching 0, it means that we are losing some long components, and we want to start from the higher signal, and ideally we want to reach 0. In this case, we need to adjust some parameters to have a better picture. And if I am satisfied with how the decay looks like, I can run the measurement with much more scans. Number of scans depends on how much time the operator has, because essentially it's a compromise between quality and time. And now we are running inversion recovery. It's for relaxation time, which is also showing us the environment and behavior of water molecules inside the sample. We are again adjusting some parameters to have the best picture. So here I also look at the signal, because ideally we want to have this zero cross part in the middle. And if I'm satisfied with how it looks, I increase number of scans and run the measurement. Usually the inversion recovery runs for hours. So here I increase the speed of the video. And while we're doing that, we can clean the lab from sample preparations. And here's my phone falling. In magic of the video making, we are not waiting 2 hours. And now finally we can process our data. So we're using UPenn for this. It's one of the ways to process the NMR data. So we're starting with the CPMG, we're setting the parameters for the program to fit our data. So the program gives us a peak with some parameters related to the peak, like signal intensity or relaxation time, and parameters related to the statistics of the fitting. And now we will do the same for inversion recovery for T1. So here again, we're changing some parameters in order to fit the data correctly. And we also have a peak, and we also have parameters related to the peak, to the sample, and to the quality of the data and quality of the fitting. UPenn gives us some output files. Firstly, it's files with all parameters saved. And also the program gives us a data file with all the data, so we can use it later on to build graphs. It gives us the fitted data, it shows us the error, it gives us the raw data, so we later on can work with it in many different ways as we want. For example, here I'm just reconstructing the same graph that the program gave me. And here we have our peak, and we will do the same for T1. And now let's go back to the lab. So we did measurements with the milk in 10 milliliter glass tube, but actually we do have different probes. It is an advantage of this type of a magnet that inside you can feed different probes. For example, we have a probe in which you can feed the whole mozzarella package with the liquid and whole without opening it, which is quite useful if we want to run measurements on the products that are relatively small without opening it. Or with the biggest coil we have, we can measure even the bottle of oil, wine, whatever we have in the lab. The process to acquire the data for mozzarella is the same as I did with the milk, so I won't be showing that. But let's see on the data processing of CPMG from mozzarella. So I'm making the same steps, and already we can see that the distribution looks quite different for mozzarella. Let's try to look at them together in one graph, so the difference between them is much clearer. So here we can see milk is a blue line and mozzarella is a red line, that they're quite different. Firstly, with mozzarella we have two peaks, which means we have different pools of spins or water in different environment. The biggest peak might be the bulk water that we have outside from mozzarella, and the smallest peak might be fat or proteins, whereas with the milk we have only one narrow peak. And now let's move to another department of physics, where we also have an NMR lab. So far we're talking about the open-bore magnets that contain an air gap between two magnetic poles. A limitation of such magnet arrangement is that the sample should be brought inside and it must fit into the limited space between the magnetic poles. In this lab, we have a one-sided magnet, also called mouse, which allows the measurements of the sample some distance from the top of the magnet. With such geometric arrangement, it is possible to measure samples of different size, geometry, and even bring the equipment to the sample. For example, here on the picture, this guy is measuring tomato paste inside the barrel. So here we're putting the sample on top of the magnet, and we will measure some volume in depth of the sample. So here with the mouse, we are recording T1 and T2 simultaneously, while previously we showed the recording of T1 and T2 separately. Such analysis can give valuable information on the interaction of water on the surface of the pores inside the sample, or, for example, transport. Also, with the mouse, we can observe the diffusion. And again, we cannot work with just raw data. We need to process it in order to observe the T1, T2 values. And here is the program for the data inversion of such an experiment. And in the end, the program gives us some information on the statistics of the fitting and T1, T2 maps. So here, for example, are T1, T2 maps of the scamorza cheese. One is wrapped in plastic and another one is traditionally wrapped in wax. And here we see that there is a difference between the T1, T2 values. Especially there is a pretty big difference in the T1-T2 ratio, which most probably indicates the difference in the molecular dynamics at the surface, or, for example, chemical exchange. And here is diffusion T2 maps. What is interesting is that we observed 3 components, and 2 of them for these cheeses are quite similar, whereas the third one is very different. And now let's return to the first lab and look at low field MRI measurements. So here you see the permanent magnet, the same that we saw in the first lab, 2 quite old computers and some coils of different sizes. Here inside the probe we are putting packaged scamorza cheese, and the probe we are putting inside the magnet. Unfortunately, with this old computer, it's not possible to record the screen. It is initially a medical instrument. The program is quite easy. There is only a few buttons, and most of the preparation that we did before are done automatically. So here again, we're setting up the measurements, and the gradient coils are quite loud. Fortunately for us, cheese was not complaining. And now, after we set up all the parameters, which is here done automatically, we can start with measuring T1 or T2. As you see here, we can measure it in 3 different directions, and by moving the line, I'm moving the sensitive volume. So I want to measure a sample more or less in the middle, and I can control it. And here we have an image inside the cheese with the signal and T1 time distribution. In order to work with the images, we also using a specific program to process the data. So again, it's one of the ways to measure a sample without opening it, without destroying it. There is no sample preparation. One of the drawbacks is this measurement is quite long. To record such a map, one needs 5-6 hours, so usually I keep it through the whole night. If your sample is changing a lot, it might influence the measurements. And finally, let's look at MRI images. So on the left, we have a cheese wrapped traditionally in wax, and on the right wrapped in plastic. Firstly, what we can see is that the signal distribution is quite different. For example, with traditionally wrapped cheese, the highest signal is inside the volume in the middle part, whereas for plastic wrap, it's opposite. So, and now you've seen almost all equipment that we are using to run measurements. And I hope this video was informative for you. And if you have any questions, please.